All right, so in the last discussion, we talked about a capacitor in an RC circuit and an inductor in an RC circuit, and they each had graphs that looked kind of like this, right? So if this was RC, I think we had a situation where this one quickly was ready to have a current right away, and then in this case, the inductor needed a lot of time to build up to its max value. And I guess I would ask us, what would happen if we ended up putting both of them on the same circuit at the same time? Well, at time equals 0, if we had a combined circuit like this, the capacitor is over here empty and ready to play ball and take charge as fast as it can. But the inductor is over here saying, nope, I don't want it. So we would notice on our current response curve a 0 here. A much longer time later, the inductor would be very ready. Please deliver current as fast as you can. I don't care anymore. But the capacitor is totally full, so it can't get any in. So we would also have a situation where the current goes to 0. So we might have to kind of supposition, what would this graph look like? And if I'm going to make blue represent my capacitor, it kind of has a case where it wants to do that. But we would have to combine it with the effects of the inductor that would want to do that. So in the end, we would get some kind of a strange curve that maybe looks like that. So you'd have a quick flash at some point where this would be I max, and then later on it would just kind of die out. So that's interesting. If we had both of these effects together, they seem to play off of each other in kind of interesting ways. So let's try a different setup. I'm going to start with a capacitor that, say, is pre-charged. And I'll connect it to an inductor, and I guess here's my switch. So at time equals 0, I'm going to close this switch and see what happens. And this is a case where if the capacitor starts out fully charged, we have something that looks like that, and we've got a lot of electrical energy kind of on the inside. And we'll define the equations for that energy a little bit later. What are we seeing in this case? It looks like there is a clear path for the charge to escape and for the capacitor to unload itself. So I've got a couple of assistants to kind of help us pantomime what is exactly happening in this. So this one is loaded with charge and ready to dump it, so there it goes. But this one is the inductor, and she's like, I don't want to see that charge at all. So it's going to put up a fight and prevent the flow of current to come out of the capacitor all at once. So maybe we should draw kind of a graph here to kind of represent what's happening. We can do two of them, I guess, right? Here is the capacitor's charge. So I'll call that Q. And then the inductor's current, we'll set down here and make I. So what's going on in this case? It will take a while for the charge to come out because the inductor is trying to fight back and says, I really would rather not see this current. So it will take a while for it to kind of represent that time constant curve that we had in the first case. And therefore, it will take a while for the capacitor to completely empty out. And in this case, we'll say it's empty. So our graph kind of switches to a new situation. The capacitor has gotten itself empty, but the inductor is fully operating and it's running. So we've got a little bit of a problem here. If the capacitor is empty, we've got magnetic field energy and there is a current that's going. So this one is perfectly happy to just say, I'm empty and totally fine, while this one's flipping her mind and saying, I don't think so. We need to kind of keep this thing flowing because I don't want to turn off in the process. So it's going to try to force this to continue going to allow it to ramp down. And that means even though we've got all of the positive charge carriers are flowing And at this point, the capacitor is empty. The inductor is reaching into the capacitor and pulling more and more of these charges off. So if it's pulling extra charges, we'll call these, and forcing them to stay in motion, that means it's causing the capacitor to end up recharging, but in the wrong direction, right? Because now our Q is negative. And we'll measure all this from what we'll call the top plate. So we have a situation that looks like this. The capacitor is being recharged the wrong way. The inductor is finally happy, of course, right? Because now it's turned itself off. But now the capacitor's in a bit of a pickle of its own because now it's charged up again. And it just happens to be charged up backwards. So we can see where this goes. This is exactly the same situation we had before, where the capacitor will dump its charge, force it through the inductor back onto this top plate, equilibrate, but now the inductor is still operating. So it's going to recharge the capacitor again and bring us back to this case. So we've got kind of a weird oscillatory kind of situation going on with our inductor and our capacitor. And we'll clean this up and make it look like more of an appropriate sine or cosine curve. So this is what's going on in the circuit. I have electric energy in the capacitor and nothing in the inductor. We're going to trade it into induction or into magnetic energy, trade it back, and trade it back. And it happens every so many fractions of a cycle. This will be a quarter cycle. This is a quarter cycle, which is 1/2 total. This is another quarter cycle later, or 3/4 total. And then this is one full cycle of oscillation back and forth to, I guess, 4/4. So this entire operation repeats. And in a perfect case, it would repeat ad infinitum, right? They would just continue trading back and forth, just like a perfect pendulum that experiences no drag force. But we know that, hey, this has probably got some resistance in the wires. There could be an external resistance somewhere in the circuit. So that effectively is a damping constant that brings our amplitude down to 0. And I think we either saw or will see that in, I think, Studio 30.1, right? There was one with the ringing down capacitor. Okay, so that's kind of the basic behavior for an LC circuit. There's some variation, a little bit of play between the time constants of C and L, and it just determines how fast is this entire cycle going to repeat itself back and forth. So let's explore that. Anything that's oscillatory, this can be a pendulum that swings, it can be a mass on a spring, right? Torsion pendulums, in this case, I guess we've got the LC oscillator. Just anything that ends up having oscillatory motion has some kind of a particular characteristic frequency, right? And we call that its natural frequency. So I don't know what this is. I'll have to think about it. For the pendulum, I think it's G over L for the bob. For the mass on a spring, I think it's K over M. And for this one, it's the square root of 1 over LC. Or if you like it better, we can call it 1 over the square root LC. It doesn't matter. Things about finding this, just to be sure that we have this right. If the natural frequency is given by 1 over LC, I could do a unit check really quickly and see, is this reasonable? This is the Henry times the farad, right? Which is the 1 over, we said, ohm seconds times a farad is a coulomb per volt. We could simplify, or I guess complexify this a little bit. The ohm is a volt per amp. We have a second, we have a coulomb per volt. Finally, some of these are starting to disappear. And let's see, what now? I've got 1 over coulomb seconds per amp. I guess an amp is a coulomb per second, right? So coulomb seconds over a coulomb per second. These are gone. This comes to the top. I get 1 over second squared, which looks like 1 over seconds. So this looks okay. Although there is a little bit of a problem. Anytime we deal with natural kinds of ratios, the frequencies that come out generally are angular. So this is really the angular frequency, not the linear frequency or the oscillatory frequency of this circuit. And that means that frequently we have these stupid rad units that just happen to pop up. I am a stickler for unit analysis. It almost always gets you where you need to go, except in cases of rads, you just have to know, oh yeah, these are a stealth, invisible kind of ghost unit that just pops in or pops out when you need it and when you don't. So if you wanted to talk about the true linear frequency in this case, well, that's really, 2 pi radians per every oscillation gives us the angular frequency, or the natural frequency would be 1 over 2 pi square root LC. So this is just something that maybe we need to keep in mind, not angular. The linear frequency would be omega divided by 2 pi. All right, so is there anything else really to talk about there? I don't think so. This is just a natural frequency, which happens. We didn't talk much about what are those energies that are being traded back and forth, so let's take a brief minute to do that now. If we have the capacitor, it stores electrical energy, right? So its total energy on the device, we said, was 1/2 CV squared. If we wanted to talk about its energy density, and that's just related to the fields, right, that fill a particular volume, that's 1/2 epsilon naught times the electric field squared. And I think by the capacitor equation, we can rewrite this as 1/2 Q squared over C, if you like that better. For the inductor, it stores magnetic field energy, and that goes by this, 1/2 L I squared. And if we really want the magnetic field density, I think that's 1/2 B squared over, I think, mu naught. And here's another case where one's in the numerator and one's in the denominator, and it just shows how these things are really similar to each other, but completely the converse. So in any cases where you might need these energies, I guess here's a table where we can kind of look at them. Okay, so on later reflection, it turns out that I think describing resonance actually does belong better here. So when we have the LC oscillator, it has a natural frequency that we know about. And really, any kind of an oscillating thing has a natural frequency, and we talked about that before. If we had a pendulum and it's about, let's say, 3 meters long or 10 feet, you know by muscle memory kind of what the period is for that, right? It's a playground swing. So if you're on it and you want to swing, if you just let it go, you know it takes about 1 second for it to go back and forth. Okay, so its oscillating period is about 1 second. So some questions that we should ask ourselves: what if you wanted to drive this thing? So you can force it to oscillate at any frequency you want, but our question is, what will give us kind of the best results? So if my assistant comes in and wants to push this swing, let's say we push it, and she kind of twiddles her thumbs over here and then comes back and pushes it at the wrong time in the cycle, obviously you're not going to get a great response out of this, right? And likewise, if she just grabs it and shakes the hell out of it at some arbitrary frequency, you know the swing isn't really going to go anywhere. The best results would be to push it and then push it as it does its frequency on its own. And that's when you get the higher and higher amplitudes for this thing to just blow up and go to resonance. So that's what we talk about when we say what happens if you were to drive this thing at its natural frequency? You're going to get the best output in the amplitude. So for a swing, that means the largest angular displacement from zero. For a spring, you're talking about something that's going to shake itself apart. And in the case of the LC oscillator, well, what is the thing that's doing the movement? It's the current in the system. So if we drive this thing at its own special natural frequency, I expect to see the current spike. And in a perfect LC oscillator, it should eventually come to equilibrium at infinity, right? Just like this swing, every cycle, you end up synchronizing it to put more energy into it with each cycle, and you're not fighting against it. So as a store, you know, ultimately, I guess our holy grail is to make the swing do this on the playground, but you know it won't, because up here in the hinge, there's a certain amount of friction. So there is a maximum equilibrium amplitude that we'll get to for steady state after the transient behavior is done. So that's what they're talking about when we say drive it at its natural frequency. You're going to get the best response, and you're at a condition we call resonance.